All right, so I guess we're going to close out our review series this semester with a discussion of math. It's kind of, I will say it's kind of interesting that we put math off to the very end, but ultimately, I think a lot of people who take the FE end up finding the math to be one of the easier topics on the exam, not because you know, math in and of itself is easy. It's just because you end up getting asked questions that are fairly basic and fairly straightforward. And there's a little bit of challenges here and there. By and large, it's not really the case. Usually you're just tested on a lot of different areas. So if you open up the manual, you end up, and go through the exam specs, you end up getting assessed in what they call only 4 areas, although these areas are pretty damn broad. For instance, the area of simply analytic geometry, that covers algebra, geometry, trig, conic sections. That's a lot right there, but they just sort of summarized their descriptions fairly succinctly. There's also calculus, roots of equations, and vector analysis, and to be honest, that's kind of all she wrote when it comes to the math on the exam. Now, I will say that there is an additional section of the exam devoted specifically to prob and stats. We probably aren't going to get to that tonight. In fact, I'm pretty much betting that we'll save prob and stats for another time. What I'm proposing is to offer, I say just a prob and stats review next semester, but I'm thinking there'll probably be a little more than that. And that's if the students are interested, if you all want. Because there's a couple topics that we didn't review in our review series this semester. One of them was prob and stats, which we probably won't get to tonight. Also, in the probability and statistics review, I think there's another topic that probably should have the quick once-over, and that's just the calculator. Making sure you all remember all the little functions with the calculator. And the prob and stats review is a perfect time to talk about that, because simple things like computing a standard deviation. If you compute a standard deviation by hand, it's not a hard calculation, but it takes a long time. And this is an exam where you can't afford, you know, to be sitting there for 10 minutes computing a standard deviation. If you can just put some numbers in and hit go and do that, just do that. So, you know, and it can also do a lot of vector analysis. It can do unit conversions. It'll get roots for you. So it's probably worth discussing that, and maybe on a mathematics part 2, if we want to call it that. Also, there's a couple other things. This probably would only take about 20 or 30 minutes, but a programming review. You will get asked like 1 or 2 questions on programming. It's mostly like flowchart stuff, making sure that you can put a number into a flowchart and get the appropriate response, but you do need to understand if-then statements and for loops and things like that. Also, while we had statics, dynamics, and mechanics of material review sessions this semester, we didn't record them. So maybe I'll record a couple sessions next semester as well. But that's really a function of if you all are interested. If you all want that, I'll be more than happy to do it. But in the meantime, I want to briefly talk about how we're going to do the review tonight. Okay, we're going to have to pause the video because the fire alarm just went off. So we'll pause this and we'll come back to it. Okay, so we are back after the excitement of the fire alarm, and I will tell a really quick, funny story. So my graduate advisor during my master's and my PhD was a professor at WVU, and you know, some people hunt, some people fish. His passion or his hobby was he's really into gourmet cooking. Like if you've ever had a meal prepared by him, it's amazing. You know, that's his passion. So if he's ever at a conference, he really does care about what he eats, and he, you know, likes to go to nice restaurants. That's some people, you know, that's not their thing. This is his thing. He likes to go to these really nice restaurants. And we went to this restaurant in D.C., and this is one of those places like that you would see in a movie, like everybody dresses up to go there, you know, hundreds of dollars per plate, you know, like really good food. And so at one point I had to excuse myself to go to the restroom, and I go into the restroom, and the restroom had one of those automatic light sensors, like you walk in and it's supposed to turn on, and it didn't. So I turned it on, and what happened next was absolutely sheer coincidence, and I found this out later, but the restaurant shared, it was a building that was occupied by several tenants, and one of the tenants was a Kinko's that was like 2 lots down, and the Kinko's was having trouble with their fire alarm. So as soon as I turn the light on, the fire alarm in the restaurant goes off. And this, you know, everybody's dressed up and in their suits, and I come in, I feel like I set the fire alarm off in the whole place. So I walk out, and my face is just pale, white as a sheet. And my advisor looks at me and he's like, "Did you do that?" It's like, "I might have." Well, dude, shut up. Keep it down. Then the chef walked around and told everybody what happened, and I was, oh, thank God. Because I thought that was me. Okay, back to math. Before we get started, I do want to take some time and review the FE reference manual. So you all have copies of all of the appropriate stuff from the manual. I really only printed off 2 handouts, one for math and one for probability and statistics. I'm just going to briefly give you an overview of what's here. So you're provided with all of the just fundamental stuff, discrete math, like stuff with unions, intersections, sets. In terms of geometry, you've got all the relationships for a line, quadratic equation, if you're dealing with a sphere, any properties of logarithms, if you're dealing with complex numbers. One thing to note for complex numbers, the manual uses J for a complex number. Like we're as civil engineers, we're used to seeing I. The reason for that is because electrical engineers can confuse that with terminology in their discipline, specifically current. You know, or I, you know, so because of that, they use J in a lot of their analysis to sort of differentiate. It makes it easier for them, so the manual kind of just adopts that across the board. Trig laws, roots of equations, let's see, all the trig identities you'd ever want, sums, ratios, squares, half-angle formulas, you name it. Basic properties of areas and volumes and what have you, circular segments, circular sectors, spheres, ellipses, parabolas. Descriptions of conic sections. So if you recall from geometry, if you take 2 cones inverted off one another, you can form all of your fundamental graphs by striking a plane through those sections. So you can get a parabola, an ellipse, a hyperbola, a line, a point, all those fundamental, a circle, all those fundamental graphs. Excuse me. Differential calculus, all the fundamental definition of a derivative and a partial derivative, other things like curvatures, L'Hopital's rule, integral calculus, just about every derivative and integral identity that you would need on the test, derivatives of sines, cosines, sums, products, differences, integrals of the same, and a couple of your fundamental integration formulas, applications like centroids and moments of area, progressions and series, and also Diffie-Q. One thing, we will have one Diffie-Q problem in this review session, and you'll find that most of the stuff you see on the exams plug and chug. This is where it starts to get a little beyond what you would need to worry about. Like I don't think you really need to worry about 4-year series. The likelihood of you getting a 4-year series on an FE exam is very unlikely unless you went general, or maybe electrical. They might see 4-year series, but you wouldn't have to worry about it. Laplace or Fourier transforms, Laplace transforms, matrices, vector identities, all that stuff. You will have to be familiar with that. Some numerical methods, but I wouldn't expect too much of that. And then probability and statistics, which I think I'm going to hold off because I think after our review tonight, we're going to be pretty well It's going to be pretty late, and I think we'll just hold off probability and statistics for another day. Sound good? All right. So here's how the review is going to go. I organized these slides so that I think I could write on the slides as we go. And what you'll see, these problems that I've selected, I was able to whittle it down to 20 problems. These problems are not, they're not anything like the problems we did, say, in structural analysis or concrete design where the problems were really, really massive. That's not really what you're going to get on this section of the test. In fact, most of the problems that you're going to see are fairly short. They're pretty straightforward. The only thing is there's a lot of them. So what I'm going to do is go through some fundamentally basic math problems, and I'm just going to sort of just do them. I mean, you know, you'll see as we're going to, oh, this is simple, because it's fairly straightforward. I'll interact with y'all a little bit, but I think for the most part, I'm just going to go ahead and knock them out. And if you all have any questions, please, you know, stop me and go, wait, what the heck's going on here? But I think you'll see that this is fairly straightforward. So with that, I'm just going to go ahead and get started. We'll start with problem 1. So problem 1, what is the length of a line segment with a slope of 4/3 measured from the y-axis to a point 6, 4? So this should be a fairly straightforward problem, because if you start off and look at the data you've been given, you know that your slope is 4/3, right? And you know that your point on the line, I guess x1, y1, is 6, 4, right? Sound good? Actually, hold on. Let me see something. Oh. Okay. I'm actually going to pause the recording for a second because I want to change my pen settings. Okay, now we're back. Let's give this another shot. So m is 4/3, and then x1, y1 is 6, 4, right? That's a little better to read, right? Okay. All right, so with that, we should be able to get an equation for the line fairly straightforwardly, right? Because this is just point-slope formula. We have a slope and we have a point. So y minus y1 is m times x minus x1. So that's y minus 4 equals 4/3 x minus 6, right? So that's y minus 4 is 4/3, and then we've got to distribute that. So 4/3 times x is 4/3 x, and then 4/3 times 6, what's that going to be? Be 24/3, so 8. So y is 4/3 x minus 4. Is that a fair statement? So far, so good? Now, let me ask you this. So let's see what I can do here. So, okay. So here's the x-axis, here's the y-axis, and we've got this point 6, 4, maybe somewhere about like that. And then we've got some line going through that point at a slope of 4/3, right? And we want to figure out ultimately where that line crosses the y-axis. Is that a fair statement? So what do I know about the y-axis? What values are true here? Well, your y-intercept. So what is true about the y-intercept? How do I find a y-intercept? Y-axis. So what my point is, what is true about x along this line? 0. There we go. So what I'll say then is on the y-axis, x equals 0. Therefore, y is minus 4. You see what I mean? My point is this, is I now have 2 points. I have this point, and I have the following point. Right? I mean, what did the problem ask for? It said, what is the length of the line segment measured with this, or with this slope measured from essentially the point 6 comma 4 to this point, right? Because that's the point where it crosses the y-axis. So now that I've got these 2 points, how am I going to determine the distance between them? Fairly straightforward, right? D is the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared, which is, what do we have? We've got 0 minus 6 quantity squared plus negative 4 minus 4 quantity squared. See how I'm doing that? Make sure that you're keeping track of your signs. So this is the square root of what? Minus 6 quantity squared plus minus 8 quantity squared, which is the square root of 6 times 6 is 36, plus 8 times 8 is 64, which is the square root of 100, which is 10. And there's your answer. Pretty straightforward, right? Not too bad. This is the type, I mean, in all seriousness, this is the type of stuff you're going to get on the exam. Everybody good? Ready to go to the next one? All right. Next problem. Okay. What is the general form of the equation for a line whose x-intercept is 4 and whose y-intercept is 6? This is a very similar problem. It's just the equation of the line. So what you have to do in this problem is you just have to recognize what information you have and what information you need to get. For instance, would this be a fair statement that I have 2 points defined to me, and those points are 4 comma 0 and 0 comma minus 6? Would that be a fair statement? So given those 2 points, what can I determine? The slope of the line. Therefore, m is change in y over change in x. And remember, you just got to be consistent. So what I'll say is the second value minus the first value, so negative 6 minus 0, over second value minus the first value, 0 minus 4. Fair statement? So that's negative 6 over negative 4, which is 3/2. Sound good? Now, if you're unsure of the general form of the equation of the line, you can do one of 2 things. One, you can say, well, I'm not worried about it, and I know that y equals mx plus b will work. So we can do that. Let's go ahead and do that. Y equals mx plus b. Now, let's see if you all know what to fill in here. M is our slope, which is 3/2, x, and then what's b? Well, think about it. When we what is it? It's negative 6. There you go. See? So you can go through and do point slope form, or you can just look at the problem and say, well, no, that is our y-intercept because they just gave it to us. And then you can say, well, you know, and this is a very valid strategy on a test like this. You can say, well, I know this is the equation of the line, but what they wanted in is the general form, which is something like this. So just use some algebra and convert this equation into a similar form. So what are they doing with all these choices? They're taking all the values and getting them onto one side, and they're getting rid of their fractions, right? So would it be a fair statement to multiply this entire equation by 2 to get rid of that fraction? And if I did that, wouldn't I get 2y equals 3x minus 12? Would that be a fair statement? All right? And then I need to get everything over onto one side. What's the easiest way to do that? Easiest way to do that is just to subtract 2y from both sides of the equation. If I do that, on the left side of the equation I get 0, and on the right side I get 3x minus 2y minus 12. Simple, right? Pretty straightforward. Y'all good? Okay. Now, next one. Okay. This one is probably a problem that you've done before, but I'm just trying to get, I mean, that's the whole point of these review sessions, is just to get your brain jogging when it comes to the wonderful world of mathematics. So now it's time to talk a little bit about logarithms. So for this problem, we need to simplify and evaluate the following expression. So if you notice, we've got a bunch of terms, but they're all base 3 logarithms. Okay? Now, if you remember, if I've got, excuse me, if I've got 2 logarithms that are added together, I can take those 2 terms inside and create a product. Or if they're subtracted, I can create a quotient. In other words, something like this. Let's just sort of rewrite the expression. We have a base 3 logarithm of 3/2 plus a base 3 logarithm of 12 minus a base 3 logarithm of 2. Now, I know you all have seen this before, so this is just sort of dusting off those memory banks. But let's start off with these 2 on the right. The base 3 log of 12 minus the base 3 log of 2. Can I do this? Can't I take these 2 terms right here and say, well, I've got this original one plus this. Remember that? Remember for your properties of logarithms that if you have a difference, you can turn that into a quotient of the terms collected inside your logarithm. So that is plus a base 3 log of 6. Right? So, pop quiz. If I have a difference and I turn those into a quotient, what am I going to do with these 2? Multiply them together. So, taking these 2, it's going to be the base 3 logarithm of 3/2 times 6, which is the base 3 logarithm of 3/2 times 6 is 18/2, or 9. Now, you can probably do this in your calculator, and that's fine, but I also want to see if you remember what a logarithm is. They even go more fundamental than all these logarithmic properties. Let me just ask you a fundamental question. If I have the base 3 logarithm of 9, and I want to determine what that is, like that's x. What is x? X is that special number such that if I take 3 and raise it to that power of x, I get 9. So look at this expression and tell me what's the answer to the problem. No, you're raising. So 3 squared. So in other words, the base 3 log of 9 is 2. And the reason why 2 is the answer is because 2 is that special number such that if you take 3 and raise it to the 2 power, you get 9. And remember, that's what a logarithm is. All a logarithm is just a rearranged exponent. Right?
I like how they put, for answer, I guess it was straight up, if you put put it in your calculator.
Yeah.
It's base 10.
You're right, yeah. Yeah. Now, there is a change of base formula that you can use, and basically you're taking you change it to like a natural log, and then it's just a ratio. But in the end, a problem like this should be, you can do it fairly straightforwardly. Is that good? Okay. All right, so one of the other points I guess I should make, there is no way that I am going to cover, how many different math classes? There's algebra, pre-calculus, trig, geometry, Calc 1, Calc 2, Calc 3, Diffie-Q. I cannot cover that in 2 hours. So what I've done is I've selected what I think are snippets of each course that cover as much material as possible. So we're sort of like, now we've sort of left out the world of algebra, and now we're jumping into the world of trig. So just be prepared. That's probably going to happen. We're going to jump from one world to another, and that because that's going to happen on the test. So, excuse me. All right. With that, let's do a little bit of trig. So for some angle theta, you've been given that the cosecant of that angle is -8/5. So based on that information, you need to determine what is the cosine of 2 theta. Now, there's a couple ways that you could go about this. One way is you could take this information and try and draw a triangle off of that, and then use that information to back calculate your cosine. I have a little bit more of an elegant approach, so let's try this. Would you agree with the following statement, that if the cosecant of some angle is -8/5, would you agree that I can, with that logic, state that the sine of that angle is -5/8? Would that be a fair statement? Okay. Now, this is where your manual comes into play, because some of these trig identities you can remember, and some of them you should just look up. So let me ask you this. Is there a trig identity in this list that we can use to just calculate this directly? We have the sine of a given angle. Can we calculate the cosine of 2 times that angle with what's on this list? So I'll put page 23. And how about, let's see, 1, 2, 3, 4. I'll say I think it's number 13. Do you see this? Now, they use alphas in the manual, but it really doesn't matter. I'm sitting here drawing an alpha. Do you see that? Right? So this is 1 minus 2 -5/8 squared, right? Which is 1 minus 2 times 5 times 5 is 25 over 8 times 8 is 64. I'm sitting here saying it and I'm not writing it. So that's going to be 1 minus, and then if I've got 2 times 25 over 64, the 64 can cancel and leave me what, 32? So (25 over 32), which is 7 over 32. Not too bad, right? Bringing it back. I know you've done stuff like this before. I know it's probably been a while. Sound good? We're rocking and rolling. Okay. This one's going to test those skills a little bit more. Okay. So the expression, the cosecant of x times the cosine cubed times the tangent is equivalent to what? All right, so this is sort of my trick for problems like this, and it's really a piece of advice that I would give for any problem involving complex trig or anything that seems a little involved, is that when in doubt, convert everything into sines and cosines. What do I mean by that? Let's rewrite the expression. Now everything's being multiplied together, so I'm putting a little bit of space between each trig function because I want to make some statements. All right, you tell me, what can I do with this cosecant function? Like, how can I edit that? 1 over the sine. I can't really do, I mean, the trick is to get everything into sines and cosines, so this stays exactly where it's at. What about this one? What can I do with that? There you go. Fair statement? Now, let's think about this. What you're really doing is multiplying each of these together. Now, can anybody look at that and tell me, when you multiply these together, what do you get? You get the cosine squared, because the sines cancel. Cosine cubed over cosine is cosine squared. So cosine squared. Now, cosine squared isn't anything like one of these terms. But what can I, let's think about it like this. What's that? Well, what is that? What's the most common identity that you remember in regards to the cosine squared? Well, essentially, yeah, because the sine squared plus the cosine squared is always a particular value, and that value is 1. So, therefore, cosine squared is 1 minus sine squared. And your answer is C. Excuse me, goodness. Well, to be honest, this is probably what you're going to get on the math portion. You don't get anything that's incredibly complex. You just get thrown a lot of, like, oh, wait, it's a line. Now it's trig. Now it's this. So that ends up happening. So, okay. This one, I think, takes a little more thought. You kind of have to look past what you're seeing on the question and sort of think a little more critically about it, which is why I kind of like this question. So on this problem, the question states, what is the value of x, a value that's less than 360 degrees, that will satisfy the following equation? You've been given the sine squared of x plus 4 sine of x plus 3 equals 0. Now, let me ask you a question. What does this equation look like? Just right off the bat, what does it look like? It looks like a parabola, or it looks like a quadratic, doesn't it? So what I'm going to do is this. I'm going to say, let's let, and I'll make it up, a equal the sine of x. If that's the case, then is this a fair way of writing that equation? So now what do you have to do with that equation? You can do one of two things. You can plug it into the quadratic formula, or we can find its roots by doing what? We can factor it, right? So we have a and something equals 0. And we have to ask ourselves, we have the factors 3 and 1. Those are going to work because 3a and 1a are going to give you 4a. And the signs tell me that those factors are positive. So that means that a plus 3 equals 0 or a plus 1 equals 0. And that gives us that a is minus 3 or a is minus 1. Is that a fair statement? Now, what does that truly mean, though? That means that, actually, I'm going to use some colors. I mean, what did we originally state? We said that a was the sine of x. So, really, this is what we're looking at, isn't it? Fair statement? Now, one of these answers doesn't make any sense. Can you guess which one? It's the negative 3. Now, there's a reason why. This is the sine of x, right? Well, you're close. You're close. Nope. Think about this. Let's sort of take a pause, okay? Let me ask you this. What does the sine graph look like? Not the cosine, the sine. It looks like this. Like that, right? Now, let's see if you all remember. What is this value right here? 180 or pi, right? We'll keep it in angles for the sake of this problem since we're dealing with that. That is 360, right? This is 270, and this is 90, right? So we'll say that this is x, and this is the sine of x. So far, so good? Now, let me ask you this. What is that y value right there? You tell me. 1, right? Plus 1. What's this value? Right there. Now, what we are looking at is a graph of the sine of x. And what you're telling me is that the sine of x goes anywhere from plus 1 to minus 1, right? So what doesn't it hit? Doesn't hit negative 3. That answer doesn't make any sense. So what I'll say is this expression is invalid. This expression on the right is only true. Oh, I'm getting ahead of myself. At x equals 270 degrees. Not too bad, right? Questions? Okay. All right. So problem 7. A little bit more into the trig, but this should be fairly straightforward. If the rectangular coordinates of a point are negative 3 and negative 5.2, what are its polar coordinates? Now, let's think about this critically, because there's there's an observation that we can make right off the bat. Looking just at the choices, what isn't the answer? Okay, well, that's possible, but let's keep in mind, what do polar coordinates represent? The r and the theta, right? What can't r be? No, r can't be negative. Like, r is a positive. Remember, when you do a polar coordinate, like what you do is, like you have your Cartesian coordinate system, And then what you're saying is for r comma theta, go out some value r, and then rotate some angle theta, and that puts you at your point of interest. So r, by its very definition, can never be a negative number. So my point is, regardless, that is not the answer. Make sense? Now, here's another interesting point about this problem. Let's go back to our coordinate system in general, right? Let's go back to this. So we go out some distance r and then rotate some angle theta, right? This direction would be rotating theta in the positive direction. Going down this way would be theta, would be a negative theta, right? So if our coordinates were like 5 and positive 30 degrees, we would go out 5, rotate 30 degrees, and that would put us somewhere like right here. Fair statement? Now, let's think about this. What are the coordinates of our given point? Both are negative. So that's going to put us somewhere about right here, right? About, right? So my question to you is, now what other choice can I eliminate? You're exactly right. That one's out too, right? So without even really doing any math, 2 of our choices are eliminated. So that's something you always want to look for on these problems, is that one of the choices can always be eliminated. All right, so it's either B or D. Do we really need to calculate the R value? Not really, but what the heck? Let's go ahead and do it. Do y'all remember how to calculate R? If you've been given an X value and a Y value, it's just that. And you can do the math, you'll see that's exactly 6. Or well, it's actually, it doesn't come out to be exactly 6. It's it actually comes out to be, let me do the math here. It actually comes out to be about like 6.02, which I guess the problems that are on these PowerPoint slides are technically not written in FE format, because usually when you do FE questions on the exam, the question wouldn't say what are its polar coordinates. It would say what is most nearly its polar coordinates. And I think what I was trying to do on all these problems was keep the text as succinct as possible so to have more room to write on the slides. Yes, they would. Now, as for the theta, how are we going to get that? Well, let me ask you this. What is the tangent of theta going to be? It is y over x, which is negative 5.2 over, point that up a little bit, minus 3. Ends up being about like 1.73. So if the tangent of theta is 1.73, how are we going to get theta? There we go. And that comes out to about 60 degrees. Now you go, wait a minute. How's that possible? Well, remember, tangents repeat every 180 degrees, right? Remember, what does the graph of the tangent function look like? Remember this? And then it actually repeats every 90 degrees. So what I can do is I can say that since the tangent repeats every so often, I can say it's essentially 60 plus or minus, you know, those even increments of pi. So it could be 60 degrees, be 180 off that, which would be 240, or it could be 180 in the opposite direction and be minus, nope, 120. See what I mean? So I'll say plus or minus in pi, because we know that's going to be correct, so therefore 120 degrees. And if you want sort of a behavioral observation as to why that works, think of it like this. Here's where your point is. What we're saying, or a behavioral observation, maybe a physical observation would be a more apt term. Basically what we're saying is that this angle here is 60 degrees. It's this angle, however, that we're interested in, and that angle is the 120. But it's negative since we're going in the opposite direction. So there we go. Does that make sense? Okay. Okay. Now, we're into the world of geometry. So now it is time, well, I guess analytic geometry, if I wanted to be fair and accurate. Okay. I want you all to turn to page 26 on this little handout. I'll even write it out here. Okay. The reason why I'm wanting you to turn to page 26 is because it involves what's going on with this problem. So this problem says determine the xy coordinates of the center of the circle defined by the following equation. So we have x squared minus 8x plus y squared minus 10y plus 25 equals 0. All right? Now, this is a circle, so it stands to reason that what we really need is the equation of a circle, which is, what is it? The following. Remember that? So on this expression, what's the center? It's a point, right? And it's defined by the coordinates h comma k, right? Remember that? So what our goal really is in this problem is to get this equation to look like that, right? So how am I going to do that? Well, to start off, let's do some subtraction. Would you agree with the following statement? I'll put therefore. Do you agree with that? All right, now what I'm going to do is I'm going to group those together. And I'm going to perform a procedure called completing the square. You all done that before? Been a while, right? So how do you complete the square? Well, you look at each of those terms individually, and or each of those groups of terms individually, and you say, well, what do I need to add to each of those brackets such that what's going on inside the bracket is a perfect square? So let's think about what's going on the left side. So on the left side, it's x squared minus 8x. So think about foiling, right? If I was going to FOIL this, I'd have, in order to get a perfect square, I'd have like a 4 on the outside and a 4 on the outside, or 4 on the inside. Like, think about this. If I looked at, let's say, x minus 4, x minus 4, and I FOILed that out, wouldn't I get x squared minus 4x minus 4x plus 16, right? See that? And that would lead into what's going on right here except for the numerical term. I've got the x squared, I've got the minus 8x, and what I don't have is the 16, right? So what I'm going to do is I'm going to say, all right, and we'll come up with a mathematical definition for the second term so that we're being consistent. I have x squared minus 8x. I'm going to add to that 16. Now, a mathematical way that we can reach that conclusion, and I mean you can observe the pattern on the first one, but for this one, watch this. If I take that 8 and take half of it, I get 4, right? 4 squared is 16. So let's look at this one. What is half of 10? What is 5 squared? 25. So what I'm going to do for the next term is I'm going to say y squared minus 10y, but I'm going to add 25. Now, here's what you've got to make sure that you do. The laws of equality state that if I add 16 to one side of the equation, I must add 16 to the other side. And if I add 25 to one side of the equation, I must add 25 to the other. So really what I've got is this. Does that make sense? So, this first term right here, how can I write that in a more simplified fashion? If I factored that. I mean, wouldn't we agree we would get x minus 4 times x minus 4? So wouldn't that be x minus 4 squared? What about this one? You tell me what to write here. So if this one's x minus 4 squared, what do I put here? Well, y minus 5 squared. But yeah, you're exactly right. Yeah. Yeah. So here on the right side, we'd end up having 16. But ultimately, that doesn't matter, because what I'm really interested in is this and that, right? So what's the answer to the problem? What's that? Or C. Everybody good? Am I ready to go ahead? Now it gets fun. We've been dancing around the topic, and now it's time to start getting real. What is the slope of the following curve when it crosses the positive part of the x-axis? So what does that mean I need to do? Find an x-intercept, but we also need to do something else. How do you find the slope of a curve? We're in calculus land. We must take a derivative. It's been a while, isn't it? All right. Okay. Let's start off with The x-intercept. Now, what is the x-intercept? It's the part where this function equals 0, right? So if I have how am I going to determine where x equals 0? No. Or where the function equals 0, not where x equals 0. Sorry, we're looking for wait. Positive part of the x-axis. This is where y equals 0. So we set y, sorry, it's late, my coffee's wearing off. We set this equation equal to 0 and we're solving for x. We want to know the value on the x-axis where y equals 0. So what do we do for this equation? Can we do that? No, we can't really factor it. So how do we solve this equation? Quadratic formula. There we go. I mean, I guess we could, but and technically the answer is yes, we can, but it gets nasty. I mean, it's fractions, and I really don't feel like dealing with fractions. And I mean, this polynomial just screams quadratic formula at you, just because the coefficients don't naturally look like they work out. That should be burned into your memories right now, or by now, am I correct? So far, so good? Right? I mean, just plug and chug. Wait. I'm getting ahead of myself. This is supposed to be, for some reason I thought that was 6. That's -3, and that's 3. I don't know why I wrote 6. So square root of 3 squared is 9, -4, 10, and -1 is +40 over 20. So that's going to be our answer, right? X is 3 plus or minus 7 over 20. Now, let's reread the problem to make sure that we're not losing focus on what we're talking about. What is the slope of the curve when it crosses the positive part of the x-axis? Which one of those answers can we neglect? I mean, keep in mind, we're solving an equation. It has 2 roots, right? Well, not necessarily. The slope doesn't necessarily have to be negative, but I'm saying when it crosses the positive part of the x-axis, we're talking about positive x values. So which of those 2 roots can we neglect? Is it the 3 plus 7 over 20 or the 3 minus 7 over 20? No. That's the one we keep. The one we neglect is the minus. So I'm saying the only valid root is x equals 3 plus 7 over 20 or 10 over 20 or 1/2. You see what I mean? Because if we considered the 3 minus 7 over 20, we would get -1/5, and that wouldn't be a valid answer because that would be on the negative part of the x-axis. See what I mean? Now, okay, we've got the value of x is 1/2 our answer? Well, no, right? No, it's not one of the choices. Why is that? We're not done. Why are we not done? Do we plug it into the original function? There you go, after you take the derivative. So we take the derivative, then we plug it in. So so now we are finally getting into the wonderful world of calculus. So what is the derivative of that function? So we take that value and plug it into this expression, right? So y prime of 1/2 is 20 times 1/2 minus 3, which is 7. This is a little bit more of an involved problem. This one takes a little more thought, but you see where we're going with it? That the point of the problem is, you determine where the function crosses the x-axis, so you got to solve it. Then you take that solution, plug it into the derivative. So you got to think about it a little bit. This one isn't as straightforward as some of the ones that will come later. Sound good? All right. What is the maximum value of this function on this interval? So let's think about this one. Let's plot out our strategy. What is the maximum value on that interval? How do we determine a maximum? Where does a maximum occur, an extrema on a graph? Well, no. Inflection points are where the concavity changes. An inflection point is where the second derivative changes. But where does a maximum occur? I mean, think about your curve. Well, okay, let's just look at it like this. So here's a graph, and here's some function, right? What's going on right here? That is a local maximum right there, right? What's true about that red line? So it's a tangent. So what is the slope of that horizontal line? 0. And how do we determine a slope? We just did that. How did we get the slope of this curve? Take a derivative. So we need to take the derivative of this. So f prime is what? You tell me what the derivative is. So we need to set this equal to 0, don't we? All right, you tell me, how would you attack this problem? Quadratic, but is there something you see here? 6, 24, and 30. I can factor out the 6. I can divide both sides by 6. Now, if I divide the left side by 6, I'm going to get 0. But if I divide the right side, 6 over 6 is 1. 24 over 6 is 4. And we get that. That one's not too bad, right? Now, do we need to quadratic formula that? What's it going to factor into? There we go. So, Now, let's go back and make sure that we're understanding our strategy. Okay. So the purpose of the problem is to determine the maximum value of that function on the interval x is less than 0. So looking at that red box, which one can we eliminate? So the problem, what is the maximum value of the function on that interval? X is less than 0. So which one can we eliminate? Positive value. So is the answer to the problem x equals -5? No. Well, okay, let's address that because you're kind of half right. So how do we find the value on the function? See, this derivative tells us where the slope is 0, but we've got to take this value, plug it into this. Okay, now, you mentioned the second derivative. The second derivative, that concavity test, tells us whether or not what we plug into this equation is a maximum or a minimum. Now, you could gamble and say it's a maximum, which it is a maximum. I'll go ahead and tell you that. But if you're little, I guess, shot or little gun shy, you want to make sure that what you're doing is correct. Let's take a second derivative. What is the second derivative? What is the second derivative? So if I plug in -5, what do I get? Yeah, you'll see what I'm doing. Now, what does the second derivative tell us? The second derivative tells us the concavity. So this is concave downward, right? So what it means is that at x equals 5, the graph is going to look something like that, right? That's x equals 5. So when I plug 5 into the original function, am I going to get a maximum or am I going to get a minimum? A maximum. So plug in. You doing the math? We'll see what we get. $7.10. Let me see. These two are minus. Or that's minus. Wait, now it's 410. Did I write something down wrong? Let me see something. Oh, now I know the problem. Okay, so first off, that's a negative, and you all didn't catch my mistake because these are all negatives. That's what it is. I'm sorry. I screwed that one up. And not on the cube, yeah. It's easy to make a mistake. It's all right to make one mistake every now and then on the FE. Just don't make a lot of them. 210. There we go. I was say I thought that was right. Sound good? All right. This is a short one. But this is one of those ones that if you know how to do it, it'll take like 5 seconds. If you don't know how to do it, it'll take you a while. You're right. So how do you evaluate that limit? What? No. That's a good point. You can't say that 0 over 0 is simply 0. You can't do that. 0 over 0 is an indeterminate form. It's like saying infinity over infinity. It doesn't really mean anything. Okay? So how do you evaluate a limit that has one of those undefined indeterminate forms? Oh, there's a way, and you've done it. I can't spell this without looking at it. Y'all remember that? So what you do is you say, if I have a limit and I plug in a value and it's going to give me something like 0 over 0, in order to evaluate that limit, I keep taking derivatives of the top and the bottom simultaneously until I get a form that is solvable. Okay? So what is the derivative of the top? There we go. Chain rule. Chain rule. All right. What's the derivative of the bottom? There we go, 1. Can I plug into this? There we go. It's 5. And it's 5 because when you plug in x equals 0, the cosine of 0 is 1. So 5 times 1 over 1 is 5. That's a simple one, isn't it? But you got to remember that. It's one of those little tricks. Just make sure that you remember. Yes, it is. It's on page 27. Like when you get to the differential calculus section, all there is really is the derivative, test for a maximum and minimum. It defines what a partial derivative is and some other things like curvature, and then L'Hopital's rule. And that's all it says for derivatives. So yeah. All right. Partial derivatives. But a partial derivative is really nothing more than a regular derivative. You just treat everything else like it's a constant. So if you're taking the derivative with respect to x, you treat everything that's not x like it's a constant. So if I take the partial derivative of f with respect to x, how do I do that? Well, let's just take it term by term, okay? So let's start off with the first one. So x squared y cubed. The y cubed is a constant. It'd be like, imagine if it was 3. I'd pull the 3 out, and then it would be the derivative of x squared, which is 2x, right? So this is going to be 2x y cubed. All right? So with that, you tell me what to write for the next one. There we go. All right. What about the next one? Sorry about dropping something there. All right. Now, how are we going to do this one? No. Well, if this one was. Yeah, if this was a sine squared, we could say, well, we can't do that. This is a chain rule like any other. So if I have the derivative of a pile of junk squared, it's 2 times that pile of junk, right? So what I have is, here, let me scooch this one in a little bit. So we've got the derivative of the cosine squared. So when I have the derivative of a pile of junk squared, it's 2 times that pile of junk, right? Times, what's the derivative of the pile of junk? What is the derivative of the cosine? No. There we go. Remember that? Now, what's the derivative of the final term? 0. It's all y's, right? Y is the constant in this expression. So cleaning it up a little bit, I got 2x y cubed plus y to the 4th plus the cosine of x minus 2 sine of x cosine of x. So what we want to do is see if this matches any of these terms here. And if you look at the choices, see how with the choices they seem to have factored quite a bit? So is there anything that we can do to factor this? Let's look at all the trig stuff over here on the right. Is there any terms that are common to both of those? The cosine. So I can pull the cosine out. What about these terms over here, the polynomial terms? How many y's? Y to the 3rd. So if I pull out y to the 3rd out of this, and I pull out the cosine out of this, what do I have? I've got 2x plus y, y to the 3rd, plus how you feeling? So far so good? Not too bad, is it? Oh, you want me to go back or are you good? You got it? Okay. Now, I really, really like this problem because if you're clever, you can just look at it and tell me what the answer is. Take a moment and take the problem in. And if you look at it, you can tell me what the answer is. It's A. Why is it A? Exactly. In this expression, you need to determine what is the result of the following indefinite integral, and you have 1 over x. Integrating 1 over x yields a natural logarithm. A is the only one that has the natural logarithm. That's the answer. That happens on the FE, especially, I'd argue that on the math section, more than any, that you have the chance of that happening. And it's something, I left this problem in here very specifically for that very reason. Okay? Now, if you want, we can go through the integration. We can say, well, how do you integrate 15 times x to the 4th? Well, it's 15 times x to the 5th over 5. So that's 3x to the 5th. And then minus 8x to the 4th over 4, that gives you that. 1 over x is natural log. Integral 7x. And then you get your plus c, your constant of integration. So you could look at, if you wanted, you could write it out. But the point is, you can, if you think about it, none of these answers would work except for A. None of them would. You can just look at it, and that's your answer. Even though at first glance they all look like reasonable choices, but they're not because of that one very reason. And it stuck out like a sore thumb, didn't it? Did you see that? All right. That's all. I'm not even going to write anything. I'm just going to circle A and move on. Now, this is one that's a little more nitty-gritty. Okay. So on this one, we need to determine this indefinite integral. And I know you all are going to love this because this is going to break out those Calc 2 skills. Because this is where you have to use those methods of integration. Now, what we're going to do is nothing fairly complicated. It's really fairly straightforward. When you look at an integral like this, the easiest way to identify it is, you got these two trig functions, right? One of them is a fairly complex one, and one of them is fairly simple, right? Like you've got a cosine squared, and then just a sine, right? But you know that the cosine and the sine are related, right? And vice versa. It's just a sign difference, right? So what I'm going to do is I'm going to do a trig substitution. Or I'm going to say, let's let u equal the cosine of x. Now, why am I doing that? What is du for the cosine of x? Well, first off, what's the derivative? Negative sine. So it's going to be negative sine of x dx, right? That little differential element. Now, if I go back to my original integral, what is that term right there, based on my assumptions? No. The underlying term. No, that's fine. Now, what is this term? There you go. So really what we're evaluating is the integral, or the negative integral of u squared du, which is what? Negative 1/3 u cubed plus c. And what is u? It's the cosine. So cosine and there's your answer. Not too bad, right? Again, pretty straightforward. I know we have been here for a little while, but I think we've only been doing the math problems for about like a little over an hour, and we're already like 14 problems in. And to be honest, think about it like this. After we've gone through and reviewed this, these problems aren't that long, are they? They're short. These are typical FE review problems. It's definitely worth mentioning. Okay. Now, this one, I wanted to throw a definite integral into the mix. And I wanted to do a simple one, but I wanted to do one that makes you have to think a little bit. So this problem says, what is the total area of the region bounded by the x-axis and the curve y equals sine of x on the interval between x equals pi over 2 and x equals 2 pi? So the first thing that I'm going to do before I even do anything, I'm going to do some graphing. That might be the absolute nicest sine function I've ever drawn. That was to say, take a picture of it. Wait, well, it's recording, so it's on there. I'll make this the image for the video. Actually, I don't know that I'll care that much about it. I've got jokes. Okay, so what is this pi? That's 2 pi, right? Remember, we were doing degrees last time. Let's do radians now. Pi over 2 is about right there, right? So really what we're after is, let's read the problem again. The problem says, what is the total area of the region bounded by the x-axis? So the x-axis, that's my black horizontal line, right? And the curve y equals sine of x, that's the blue line, right? And it's saying between pi over 2 and 2 pi, right? So really what it wants we're talking about that shaded area right there, aren't we? Now, here's where things get a little, how shall I put it, delicate. Because if you remember from calculus, and this could drive you nuts on the exam, if you just integrate from pi over 2 to 2 pi, you will get an incorrect answer. And the reason why is because your integral will assume that this is positive area and that's negative area, right? So this is how you're going to have to do this. You're going to have to say that your area is the integral. And if you want, you can do absolute values for both of them. I don't know. There actually, I think there is. May I see it? Let me see. Oh, that could have been bad. Right here, above the hyperbola sign, or the hyperbolic function. See it right there? Your shift function. Now, two things I'll state since you actually brought up the Casio. If I inspect the Casio, you know that the Casio will do definite integration, right? So you could just do this problem in the Casio right now. In fact, why don't you do it and tell me what you get? I think Mr. Holliday's already working on it. Well, while you all are working on that, I can go ahead and just do the grunt work here, because the integral of the sine is the negative cosine. So what was the way? I'd check your values. Huh. Is that what you got? Oh, no, that's fine. Because if I calculate this out, so let's see, I take the cosine of pi and then the cosine of pi over 2. So let's recall the graph for the cosine looks something about like this. It goes something like that. That, and then that all the way over here. So this is 1, 0, minus 1, 0, 1, right? For your values. So what do I have? I've got the absolute value of, what is that, minus, hold on, minus that pi, so minus 1. Here, this is what I'm going to do this. Keep it simple. Let's take the negative completely out of those brackets. So I'm just dealing with the cosine of x. So it's minus 1 minus 0 plus, take the minus out, then it's 2 pi, which is 1 minus minus 1. Now, this was a cruel problem on the signs. I'll be the first person to admit it. Absolute value minus inside the brackets. That's going to be 1 minus minus 1, 2. Excuse me. So essentially all you've got is 1 plus 2. So your answer should be 3. Check that, sorry, check that again on the Casio. Let me see. You're doing, again, you're doing pi over 2 to 2 pi. You can't do that. You have to go to pi over 2 to pi. See, that's the whole point. See, what you're doing is you're just integrating straight. The problem is that the way the math works out is you're taking this area, and they're canceling. And then all you're getting is this, and it's giving you -1. What you've got to do is this. Okay, watch this. All right, so I'm going to go from pi over 2 to pi. Okay, so that's 1. So inside this bracket is 1. Okay, see what I mean? Then your next one is, where's the pi button? I'm used to a TI. I'll be the first person to admit it. Oh, whoa, I lost it. What? See, so watch this. So that first integral gave you 1. Then this one gave you -2. So it's the absolute value of 1 plus the absolute value of -2. So that gives you 3. Is that what you got? All right. Does that sound good? Is that good? All right. Now, I know that this was your favorite class, right? You love that one, right? Diffie-Q. Oh, yeah. I know students love Diffie-Q. I enjoyed the class when I took it. Well, I can understand that. Okay. Now, you're going to laugh when I say this, but this is sort of my point that I would make about a differential equation on the FE. There are so many students, and I've seen this a number of different places. They look at a problem like this, and they go differential equation, they go, pick C and move on. You know, I know that happens, but I promise you, this is not that bad, especially if you use this. Turn to page 30. What the heck was that? Somebody's making noises in the hallway. Okay. If you're on page 30, look at this. Let's read the problem. What is the general solution to the following differential equation? Y double prime minus 8y prime plus 16y equals 0. Look at this second column here on page 30. Second order linear homogeneous differential equations with constant coefficients. An equation of the form y double prime plus ay prime plus by equals 0 can be solved by the method of undetermined coefficients. So if I want, just for the folks watching the video, I can, let's see, pull that up. So I'm on page 30 of the the reference manual, and I'm looking right here on the reference manual. It says second order linear homogeneous differential equation, and it basically just tells you step by step how you need to solve this problem. Okay, very straightforward. So, and this is no different than what you do in differential equations anyways. You set up a characteristic equation based on the coefficients of these derivatives. So your characteristic equation, here I'll do this, let me, for completion's sake, I'll say page 30. I'll say my characteristic equation is r squared minus 8r plus 16 equals 0. So what are the solutions to that? Well, yeah. So we have r equals 4, and it's a double root. Now you can go through and remember your diffEQ and if you remember from diffEQ, you'll know that you'll get real repeated roots, and your answer is essentially B. Okay. But if you don't remember the diffEQ, that's the whole point of the manual. So let's go off of this. Let's see. Would you agree that from the form of this differential equation, would you agree that A is minus 8 and B is 16? So from these, would you agree that A squared is 64 and 4b is also 64? Because of that, you are dealing with a solution that is critically damped. Well, this actually starts to get into the world of vibrations, but to sort of pull the manual back up and make sure we're all on the same page. So going back to the manual, an equation of the form y double prime plus ay prime plus by equals 0 can be solved by using the method of undetermined coefficients. So we know what A is, we know what B is. And it gives us right here down on the lower part of the page, it straight gives us 3 potential options. Either A squared is greater than 4B and we have an overdamped system. We have A squared equals 4B and we have a critically damped system. Or we have A squared is less than 4B and we have an underdamped system. We're dealing with one that's critically damped, right? And if we're critically damped, what does it say? C1 plus C2x times e to the rx. And r in this case is 4 because that's what we solved. So C1 plus C2x e to the 4x just by observation. There's your answer. That's it. So what I hope is that when you get to that point on the exam, you don't just throw the test up in the air and say C, because it's not that difficult. That's the whole point. Now, does this bring you back into the world of statics or calculus or physics? A little bit of everything, isn't it? I'll say dynamics or Calc 3, yeah. So we've got vectors now, and vectors are technically they are a mathematical topic because they're the means of expressing scalars and directions in 3 dimensions. So we have a vector. Well, we actually have 3. We have A, B, and C, and we want to calculate the following mixed product. So we want to cross B and C and dot it with A. So remember, dot products ultimately yield a scalar, a number. Cross products will yield another vector. Okay? Now in this case, what we're going to have to do is cross the ones on the inside and then dot the result. So Let's see if you all remember the rule of Saris. You all are like, what? I don't know, unless maybe you're not. When you did cross products, did you ever hear that term, the rule of Saris? I'm sure you've seen, you'll know exactly what I'm talking about. So if we want to do B cross C, what do? We have I, J, K. And then we write down the coefficients for B and C. So, was it 1, 2, 3, 3, 4, and 5? And we take that determinant, right? And then the rule of Saris states that in order to take that determinant, we take those two and write them over, right? Then you take all your products going this way minus all of your products going this way. Remember that? Been a while, hadn't it? So for your I terms, what do we have? We've got 2 times 5, which is 10, and then 3 times 4, which is 12. Y'all see that? So 2 times 5 is 10, 3 times 4 is 12. So that's going to give us minus 2i. For the j terms, what do we have? J, we've got 3 times 3 is 9, right there. 1 times 5 is 5. 9 minus 5 is 4. Y'all see that? Tell me what the K term is going to be. Well, hold on. Let's see. We've got the 4 here, right? What do we have here? There you go, -2. See that? The rule of Saris is that rule that you can take those 2 rows and write them over here and do that. That's what the rule of Saris is. So, random, useless trivia, I know. So, minus 2k. All right. So, what we just did is we crossed B and C, right? Okay? So how do we continue the problem? We take this and dot it with A, right? So how do we do, maybe I should be consistent and put my little symbology there. How do we dot these 2 vectors? Like, how do we do that? Y'all remember how? Exactly. That's exactly right. You just take this times this times that, that times that. So what are we going to do? We're going to do 6 minus 2, 8, 4, 10, minus 2. You see how I did that? Because I'm basically just doing that times that. I'm doing that times that. And I'm doing that times that. See that? So, let's do some arithmetic. 6 times 2 is minus 12. 8 times 4 is 32. 10 times 2, negative 2, is minus 20. What's the answer? Zero. That was by design. Everybody good? Good? Now, some more work. We've only got 3 more problems, so we're doing pretty good. What is the angle between the 2 given vectors? Y'all remember how to calculate the angle between 2 given vectors? Do you need to remember how to calculate the angle between 2 given vectors? What's that? You have a book full of hundreds and hundreds and hundreds of formulas. Let's refer to the book. So let's see. What page do we need to go? We passed Fourier series. Okay, page 34. What do we got? We've got 2 different ways that we can handle this. But if I look here on the second column, we'll just keep it, for the most part, we'll keep it fairly straightforward. Actually, you know what? No, let's do this. Let's keep it even simpler. Okay. I'm actually going to pose this question to you all, and you tell me which is the easier method. So let's start off with the column on the right. Okay? So what we've got is, on the column on the right, it defines for us what the cross product is. It says the cross product of a vector product of magnitude BA sine theta, so forth. Why don't I just pull up the manual, make it simpler. Oh. Wait. Oh. Let's see. There we go. So here on the top right, it says, it defines for us what the cross product is, but then it also gives us this definition down here that it says the cross product is also defined as the magnitude of A, the magnitude of B, the unit vector perpendicular to that plane, and then the sine of theta. So that theta is the angle between the 2 vectors. You can see that up here, right? You're right. Well, but what, I mean, think about it. An absolute value is also another means of expressing magnitude. And that's what magnitude is. So now, what I also want to do is look on the bottom of this page. On the bottom of this page, it defines a dot product. And it says that the dot product of 2 vectors is also the magnitude of those 2 vectors times the cosine. Now, you know, from the last problem, you know how much work goes into a dot product and how much work goes into a cross product. If I wanted to determine that angle theta, what do you think is easier? Should I use a dot product or a cross product? The dot product, absolutely. So much simpler. All right, so let's go back to this. So let's keep this simple. All right. So what is A dotted with B? How am I going to do that? It's going to be what? 4 times 24 plus 12 times minus 8 plus 6 times 6, right? Now, the first one's 96, this one's negative 96, so they cancel, and that just gives us a value of 36, right? Okay. Now, we also need to get the magnitude of A and the magnitude of B. How do we get the magnitude of a vector? Remember, a magnitude is essentially the vector's length. So would you agree that the magnitude of A is going to be that, right? And if you plug and chug, you will get a value of 14. for B, you end up getting a value of 26. So to keep this simple, the magnitude of A times the magnitude of B is 14 times 26, which is 364. Is that a fair statement? So from our definition of a dot product, A dotted with B is the same thing as saying the magnitude of A times the magnitude of B times the cosine of theta. So therefore, the cosine of theta would be that dot product divided by those magnitudes. Ooh, so now writing magnitudes not even. Writing my message. So this is 36 over 364. So if I have the cosine of theta is 36 over 364, how do I determine theta? Inverse cosine, right? Yep. There is. I mean, there's a lot of different methodologies. I mean, think, in 20 questions, well, we haven't even finished the 20 questions, but we've taken one hell of a trip, haven't we? From algebra all the way to calculus, integrals, trig, whole 9 yards. So what is this answer going to be? Remember, it's got to be in degrees. You just got to do this part right here. This is this part. What'd you get? B. Yeah, 84.32 degrees. Did you get that? Well, when you get your answer, just multiply by 180 over pi. Got it? Okay. Good? 2 more problems. I wanted to at least just throw one straight matrix problem on the handout. If I had to go back and recreate these slides for tonight's lecture, I probably wouldn't have done this problem because we just did a determinant. I'd probably do like a matrix multiplication or something. But we have it, so we might as well just go ahead and do it. I mean, this is going to be a fairly straightforward problem. If I want to calculate the determinant of A, it's just the determinant and then I apply the rule of Serres again. So it's no different. So I'll let you all do the math. You tell me what the answer is. This is one you'll want to do in your calculators. So start off with the blue numbers. So 2 times 6 times 9, 3 times 7 times 7, 4 times 5 times 8. Like all those need to be added. See what I mean? All right. Here, you do the positives, you do the negatives. How's that? We'll keep it simple. So you're going to do like 3 times 5 times 9, 2 times 7 times 8, 4 times 6 times 7, right? So it's going to be all of your numbers positive minus all your numbers. Yours are going to be negative. Okay. Let me see your calculator because that doesn't look right. Let me see. Oh, okay. $4.15. What'd you get? What did you get? Well, you're going to do like what my point is all the blue numbers minus all the green or all the red numbers. So you're going to do 3 times 5 times 9, 2 times 7 times 8, 4 times 6 times 7. Like what's the sum of all of that? So what's 415 minus 415? 0. I mean, after the last problem, y'all should be able to do that. I tell you what, how about this? We'll do this. Let's do another matrix problem. Well, I'll let y'all work on this for a second. I know there is one. I figure this is simple enough that we can just do it by hand. Did you get it? All right. What do you say we do this? Okay, so here's a matrix problem. I'm joking. Funny stuff, right? You're like, don't even joke about that. All right. Last but certainly not least is the concept of a geometric progression. Okay. So this is the last problem because I think it's, I'll say this, I think after like my experience with a lot of, interacting with a lot of engineering students, this is the topic in Calc 2 that they seem to like the least, which is series. And a lot of students didn't really like that very much. And that's fine, I can understand that, even though this isn't technically a calculus topic. But I again want to kind of make that generic point that in the end, you can go to this and everything's here. Everything's here. Okay? So, it says right here, second and sixth terms of a geometric progression are 3/10 and 243 over 160. So what's the first term? So what we've got is, if you want to draw this out, you can. 1, 2, 3, 4, 5. Geometric. See, it says right there. No, that's fun, and that's definitely something that it's really easy to go, whoa, wait, what are we talking about here? Because that matters. That really, you have to know that. So this term is 3/10. This term is 243 over 160, and we're looking for that term. Okay. Okay. So far, so good? So let's go to the manual, specifically to, let me see. I'm on page 29. Past all this Fourier transform and Fourier series. Excuse me. Okay, to right here. So we're dealing with a geometric progression, and we need to determine whether a sequence is geometric or not, and we already have that. So we've got a couple terms that have been defined for us in a couple of different formulas. So let's look at this. The first term is A. Isn't that what we're after? We're after A, right? The common ratio is R, the number of terms is N, the last or nth term is L, the sum of N terms is S. Let's just keep this simple. All right. So I'll say page 29. And I'll call it L is A times R to the N minus 1. That's what it is, right? So far, so good? Would you agree that if I named these terms according to this, like this would be L2, L3, L4, L5, L6, and this term here would be L1, but we have a special name for it, and we call it A, right? That's the first term, right? So ultimately, we need to determine what these are, right? So would you agree that L2, according to this formula, is A R to the 2 minus 1, which is A to the R, or AR, sorry, not A to the R, just AR. And L6 is AR to the 6 minus 1. AR to the 5th. Now, this is going to sound repetitive or redundant, but I'm going to do something. Let's just see if what I'm about to do makes sense. So these expressions that I just derived are formulaic expressions for each of these terms, right? Now watch this. Would you agree with the following statement that if I took L to the 6, or L6, divided it by L sub 2, that's AR to the 5th, AR, which is R to the 4th. Would you agree with that? Think about what this is saying. It's saying that the ratio of the 6th term to the 2nd term is R to the 4th, which makes sense if you think about it, because look right here in your box. How do you get from L3 to L2? You multiply by R, right? That's what a geometric progression is. You keep multiplying by the same number over and over again, right? Like a geometric progression might be something like 1, 2, 4, 8, 16, 32, etc., right? How do you get, what's the R in this series up here? It's 2, because you keep multiplying each term by 2, right? So look, to get from L3 to L2, you multiply by R, right? To get from L4 to L3, you multiply R, so that's R squared. R to the 3rd, R to the 4th, right? So what I have determined is that hold on, my color's right, L6 over L2 is R to the 4th. That's what I've determined, right? Would you agree then that L6 over L2 is 243 over 160, 3 over 10? Dividing fractions means you flip and multiply. So, doing a little bit of canceling, that becomes 1, that becomes 16, that becomes 1, that becomes 81. So 81 over 16. Now this also equals what? R to the 4th, right? So how do we determine what R is? 4th root. So what is the 4th root of 81 over 16? 3/2. So therefore, R is 3/2. Let's verify that calculation that Mr. Moore just did. All right. 3/10. What is 3/10 times 3/2? 9/20. Do you agree with that? What's 9/20 times 3/2? There you go. What about the next one? What if I do the next one? 243 over 160. So, how am I going to get back to the first term? What do I need to do? And if I divide, what's my pattern going to give me? Like, what does my numerator keep doing? My numerator keeps increasing in factors of 3. So 3 divided by 3 is going to be 1, right? What's going to happen to my denominator? What's the pattern tell me? That's not too bad, is it? Well, it could, yeah, it could. Well, yeah, I mean, you could just keep going. But that's the whole point, is that, and I guess that would be my large message behind what it is I'm trying to get across to you all with this lecture tonight, is that, yeah, there's a lot of stuff on the FE when it comes to the math section, but ultimately 2 things will always be true. A, usually the questions you get are fairly fundamental. B, if you're unsure, it's in the manual, I promise. And you all are sitting here looking through these paper copies of the manual. You'll be able to search a PDF when you take the test. What do you think? All right. I don't know about you all, but I'm thinking save prob stats for another day because, yeah, I'm getting tired. Ooh. Y'all good? All right, let's go ahead and close this out.